Dear students, in our previous lectures we have seen that the EMF induced per phase of stator and rotor of an induction machine is given by E1 is 4.44 F1 phi N1 kW1 and E2, the rotor induced EMF per phase, is 4.44 F2 phi N2 kW2, where we know that the frequency of the rotor induced EMF F2 is given by S times F1. And at standstill we know that the SILP is equal to 1 and hence F2 will be equal to F1, and the EMF induced at standstill per phase of rotor will therefore be given by E2 will be equal to 4.44. We'll have here F1 into phi N2 kW2. If we take the ratio of E1 to E2 with the rotor standstill, it will be obviously equal to all other terms will cancel out except for n and k's. So we'll have E1 by E2 will be equal to N1 kW1 by N2 kW2, which can be written as, since N1 is a constant, kW1 is a constant, and similarly in the denominator we can write it as N1 prime by N2 prime, which is a constant A. Therefore what we see is the ratio of the stator induced EMF per phase to the rotor induced EMF per phase is a constant, and we know that this type of relationship holds good for a transformer, and therefore we conclude that an induction machine at standstill behaves like a transformer with a transformation ratio N1 prime by N2 prime, where N1 prime and N2 prime are known as the effective number of stator and rotor turns per phase. Let's now describe how the torque in an induction machine is developed. For this, let's consider a two-pole machine with a rotating magnetic field rotating in the counterclockwise direction as shown in this figure. Let's initially assume that the rotor is standstill and the rotating magnetic field in the air gap is aligned as shown in this figure with the axis of the field along this line. For the situation considered, therefore, we can easily see that if we see the conductors in the left half of the rotor, they are under the influence of the north pole, and the north pole is moving in the counterclockwise direction. We see that at the center of the north pole, if we consider a conductor at the center of the north pole, the velocity of the conductor relative to the field is upwards, V, and V is directed towards right. And if we apply V cross B rule, we can easily see that the direction of the induced EMF will be into the plane. And if we similarly consider all other conductors in the left half of the plane, we will see that the EMF induced in all the conductors under the influence of the north pole will be directed inwards. And using the same procedure, we can see, if we consider a conductor at the center of the south pole, we can see that the velocity of the conductor relative to the field is downwards, V, B is directed towards right, and therefore using V cross B rule, we can see that the EMF induced is directed outwards. And so will be the case for all other conductors under the influence of the south pole. So this shows the direction of induced EMF in the conductors of the rotor at the instant considered. The magnitude of the induced EMF will depend upon the flux density, because it is given by BLV. V is constant, L is constant. Therefore, it depends upon B at each and every point, and we can easily see that since the magnetic flux density in the air gap is sinusoidally distributed, the magnitude of the induced EMF will be maximum along the center of the North Pole, and the EMF in the conductors will decrease gradually to zero midway between the poles. So this figure, let's label this figure as figure 1. It shows the EMF induced in the rotor conductors, induced in the rotor, figure 1. Now let's assume that the rotor circuit inductance is 0. Inductance equal to 0. Therefore, what will happen? The rotor induced EMF will give rise to currents in the rotor conductors, and those currents will be in phase with the induced EMF. So rotor currents will be in phase with the EMF induced in the conductors, and therefore the current distribution in the conductors will be similar to the EMF distribution, and we can draw it here. So the currents in the rotor conductors under the North Pole will be directed inwards, and those under the South Pole will be directed outwards. So if this figure shows, this is figure 2. This shows the current distribution in the rotor conductors. Now we have current carrying conductors and we have a magnetic field. Therefore, each conductor will experience a force, and we can determine the direction of the force by using I cross B rule. And if we have a look at a conductor under the influence of the North Pole here, the current is directed inwards, B is directed towards right. Therefore, using I cross B rule, we can see that the force developed will be downwards for the current considered, and similarly on this side the current is directed outwards, B is directed towards left, towards right, and therefore using I cross B we can easily see that the force will be directed upwards. If we consider these two conductors, we see that they will give rise, the two forces on the two conductors will give rise to a net torque in the counterclockwise direction. And if we apply the same rule, same procedure for all other conductors, we'll see that the forces on the conductors are such that the net torque developed is in the counterclockwise direction, which is the direction of the rotating magnetic field. So we see that the torque on the rotor is in the direction of the rotating magnetic field. Now we have assumed the machine to be standstill initially, and now there is a torque developed. If the torque developed is more than the opposing torques, what will happen? Under the influence of the developed torque, the rotor will accelerate. It will start rotating in the direction of the rotating magnetic field, and as it gains speed, the relative speed between the rotating magnetic field and the rotor will decrease. The EMF induced in the rotor conductors and hence the currents will also decrease, and the motor will continue to accelerate and ultimately it will reach an equilibrium at a certain speed at which the EMF induced in the rotor conductors is sufficient to cause a current to flow in the conductors that produces a torque equal to the opposing torques. So this is how how the motor will reach an equilibrium point and it will continue to rotate at a definite speed. But as long as there are opposing torques, the motor speed can never reach synchronous speed, because we know that at synchronous speed the slip will be equal to 0 and hence no EMF will be induced and no torque will be developed. Therefore, the motor can achieve a speed which will always be less than synchronous speed. Now, if we consider the rotor to be moving in the clockwise direction, we can still think of the rotating magnetic field to be moving in the counterclockwise direction relative to the rotor, and therefore the situation will be similar. As far as the direction of the torque developed is considered, the torque will still be developed in the counterclockwise direction, that is in the direction of the rotating magnetic field. So what we conclude is, for the rotors to be rotating in the direction of the rotating magnetic field at a speed less than synchronous speed, or moving in the direction opposite to the rotating magnetic field, the torque will always be in the direction of the rotating magnetic field. But if we consider now the rotor to be rotating in the direction of the rotating magnetic field at a speed greater than synchronous speed, in that case, what will happen? The relative speed between the rotating magnetic field and the rotor will reverse. That means, although the rotating magnetic field will be moving in the counterclockwise direction, the rotor, since it is moving at a speed higher than the rotating magnetic field in the counterclockwise direction, we can think of the rotating magnetic field to be slipping in clockwise direction relative to the rotor, and hence the direction of the induced EMF in the conductors will reverse and the direction of currents too will reverse, meaning thereby that the direction of the induced torque will be in the clockwise direction. We can conclude that the torque is developed in the direction of the rotating magnetic field relative to the rotor, or in other words, the torque is developed in a direction that would push the rotor speed to be close to the synchronous speed. So let's note down the conclusions that can be made. We see that with the rotor rotating in the direction of the rotating magnetic field at a speed less than synchronous speed, or with the rotor rotating in the direction opposite to the rotating magnetic field, the torque is developed in the direction of the rotating magnetic field. And if the rotor is rotating in the direction of the rotating magnetic field at a speed greater than synchronous speed, the torque is developed in opposite direction of the rotating magnetic field. And this can be summarized in this statement that the torque is always developed in the direction of the rotating magnetic field relative to the rotor structure. This is to be underlined here, is the direction of the rotating magnetic field relative to the rotor structure. The torque developed tries to decrease the relative speed between the rotating magnetic field and the rotor. That means this torque always tries to push the rotor speed to be close to the synchronous speed. Now we have seen that when we have considered a rotating magnetic field rotating in the counterclockwise direction, the EMF induced in conductors under the influence of north pole is inverse, and the EMF induced in the conductors under the influence of the south pole is outwards. And we had initially assumed the rotor inductance to be equal to 0, and for that case, the currents in the rotor are in phase with the EMFs induced in the conductors, and therefore the current distribution is same as the EMF distribution in the conductors. Now, as the currents flow in the rotor conductors, they will establish a field of their own. And if we use the corkscrew rule, we have here on the left side the currents will be flowing into the plane, and if we rotate a screw so that it should advance into the plane, it has to be rotated counterclockwise, and on this side it has to be rotated counterclockwise. Therefore, the rotor currents will establish a flux which will be directed downwards. In other words, we can see that in the lower half of the rotor, there will be a north pole developed and a south pole will be developed in the upper half of the rotor. Let's show it here. The center of the north pole of the rotor will be here, and the center of the south pole of the rotor will be here, and therefore we see that the rotor field will be directed downwards. The stator field is directed towards right and the rotor field will be directed downwards, and therefore we can show the relationship between the two fields. We see that the stator field MMF can be represented by means of a vector. This is known as a space vector along the axis of the field, and the rotor field can be represented by a vector along the axis of the rotor field. This is here F, this is Fs, and here we have F, R. Therefore, what will happen is there will be a relative angle of 90 degrees between the two fields. Now, as the rotating magnetic field, stator rotating magnetic field rotates, what happens? The distribution of the EMFs and the currents in the rotor will follow the rotating magnetic field, and therefore as the rotating magnetic field rotates, the EMFs and currents also follow the rotating magnetic field, thereby that the rotor field will also follow the stator field, and there will be a relative phase displacement of 90 degrees always. So when the rotor inductance is neglected, therefore what we see is that the rotor field follows the stator field with a 90 degrees separation between the two. And one more thing that you can see is that the rotor field will be lagging the stator field. Now, so this was the situation with the rotor inductance neglected. So this is the let's write it down here. This is figure 3, shows the magnetic field due to rotor currents. With LR equal to 0. Now, we know that the rotor conductors should have some inductance, and therefore with LR included, what will happen is the currents induced in the rotor circuit will not be in phase with the EMFs, but the currents will be lagging the EMFs by an angle which we call as the rotor power factor angle. So the currents, rotor currents, lag the EMFs by an angle called rotor power factor angle phi, and therefore we can show the distribution of the currents with LR included. So we see that with the rotor inductance included, we see that the currents in the rotor conductors are lagging their EMFs. EMFs have a center line here, dividing line here, but the rotor currents will have a dividing line here, and therefore the rotor field will be directed along this line, and the stator field is directed around this line. Therefore what we see is that the rotor field now will be lagging the stator field not by 90 degrees but by an angle greater than 90 degrees. This would have been the case if LR was equal to 0, but now there will be an additional angle phi, which is the rotor power factor angle. Therefore with LR included, the effect of the rotor inductance is the effect of the rotor inductance is to cause the rotor field lag the stator field by an angle 90 plus phi, where phi is the rotor power factor angle. So we'll conclude this lecture here. Thank you.